Today I am going to give this talk on behalf of Okay, this is work done by Manya Bansal. Unfortunately, she couldn't be here, and all my co-authors also decided not to come. So I got unanimously elected to give this talk. So I'm going to talk to you about lightweight, locality-aware composition of black box subroutines, a build system we call Fern. So let's start by looking at how do matrix multiply. You want to do very high performance matrix multiply. You can, if you want, go write these 5 lines of code. This is something even undergrad can do easily. The problem is, if you write these 5 lines of code, you get matrix multiply. It runs really, really slow. The fastest matrix multiply you can get in a library is, in this case, for large matrix size, about 600 times faster. So the reason it's 600 times faster is this fast matrix multiply has been written with hardware in mind. A lot of work has been done to make sure that matrix multiply really fit into that hardware. First of all, it's tiled, so the data that you bring in will stay in cache and use multiple times as much as possible. It's vectorized, so vectorized gives you most amount of flops, so you get the maximum flops out of a processor. Obviously, modern processors have multiple cores, and you might even have multiple chips. So you want to parallelize it to get the best performance out of that. You might even want to do cache blocking, so the instruction cache doesn't overflow, everything fits in the cache. And if there are any pipeline stalls, you might want to reorder the instructions in a way that there's not going to be any pipeline stalls, so you can get software pipeline. This is great, and this is not that easy to do. I don't know whether Vikram will agree, but something like LLVM compiler is not able to get this kind of performance today. They will do a good job, but not at the level that completely utilizing everything available in modern hardware, and on top of that, the hardware also keeps changing. If you want to get there, you can get a domain specific compiler for very tiny domain that will only work with certain very specific class of functions, and they are for certain architectures that will do really well. If you really want to do it, basically do hand optimized libraries. That's what everybody do to get high performance. In fact, you go out there, there are hundreds of libraries written by manufacturers of processors, different vendors, open source libraries that is trying to give really high performance as much as possible. And this is where most of the time when you want high performance, people end up. The reason this works is these libraries can take the most important set of kernels and implement those kernels. And you can build more complicated functions by composing these kernels together. So this is the ultimate part in actually computer science to this composition is what we can build very complicated programs out of. And so what you can do is these kernels can be taught as black box functions. They can be implemented by hand, domain specific compiler, or any other way you can do that. And composing them, it's opaque. You don't have to know how that got implemented. You can do that. So let's take an example. So here's a very simple function. These functions take 2 vectors and do outer product of those vectors and get a matrix, scale the matrix, and then accumulate into the original matrix, but also scale the original matrix out. This is a common enough function, and we want to run this, and of course where it run matters. So I want to run it on an Apple machine. In fact, I want to run it on an M1 chip in here, because we have heard that M1 chip has lot of built-in accelerators. Of course, Apple had told anybody what's in there, but there's a lot of cool things supposed to be in there. So you want to do that. So how do you do this? Luckily, there are a couple of libraries there. There's like the ARM performance library written by ARM. They probably not have access to all the Apple hidden secrets in there, but they know enough of the ARM processor, because it's ARM based processor, they can do that. And also Apple has Apple Accelerate library to run this kind of code. So if you get the ARM performance library, luckily this exact function has implementation. So you can go there, find that exact function call, figure out how the arguments are, and that is all you need to do. You are done, you get in there, really great. However, if you look at Apple Accelerate library, it is a little bit smaller, it does not have this exact function in there. But what it has is two different functions, that one function that do the outer product and the one function do the accumulate. So, not bad, I can just put them together and I can get the exact performance in there. So, I just have to compose two highly optimized functions and you get there. But there is a small problem in here. When you run, the performance is not the same. The Apple Accelerate library is about 30% worse than the ARM Fused library. So, in fact, the low is better because low runtime in here. So, what is happening here? Why is it that some using very highly optimized one kernel versus two, you have performance difference? So, one possibility might be the most computation time is going to do this outer product. Outer product is slow in the Apple Accelerate library. So, let us go look at Apple Accelerate library outer product. No, its outer product is really fast because outer product is a very important function, and I think really good programmers in both companies have really implemented it well. So, this is doing really well. So, that is not an issue in here. So, what can be the issue? The main issue there is when you call these two functions, the first function will run through the entire tensor, and by the time you are done, large part of the tensor is outside the cache, and the next thing has to all load in back in the cache. So, there is a lot of cache misses happening between those two. So, that is why you have a 30% overhead. So, one solution might be to say, hey, let us go fix the Apple Accelerate library in here. It is a very simple fix, just basically do the multiply, just instead of just storing it, just multiply the scale the value and then add it in there, store it in there. Simple fix. The problem is I do not have access to this library. It is very super secret thing that it is calling this even unspecified accelerators in there. I do not know what it is even doing. So, I cannot do this in here. So, what solution do I have when I cannot go modify a library? One thing is, instead of running this for the entire data set, I can chunkify the data. I can say, hey, instead of calling the entire matrix, I can call it to multiple chunks. So, what I can do is, instead of this code, I can create bunch of small tiles, column tiles in here, and then basically call each tile by tile for the first function, and when it is done, feed it to the second function, voila, you get the results, and you have a chunkified code in here. You can do that, and then you can iterate through all the tiles in here. Intuitively, now we are doing lot more function calls. So, you can think the function call overhead might be bad. Oh, by the way, this is what you call fusion. Okay, we knew that for last whatever 40, 50 years to do, but now here is a case that we are doing that. And what we find is even there is function call overhead, this actually get really good performance. So, what that does is because the chunks are still in cache before the other thing is called, I do not have the cache problem in here, I get the overhead. The second observation is naive function composition result in locality losses, because you run the entire thing to the end, and then you when you do that, your cache, you have a lot of cache misses, is not good. So, can you do some simple composition? So, what you have to do in this case is, instead of running the entire thing, I basically run this in small chunks. So, that I have to have the entire column and part of the row, and produce and basically produce chunk of that and keep doing chunks in here. And if I can do that, I can get this chunk execution. The issue is right now I have this black box 2 implementation. That is not that is possible to do this chunkification. So, one possibility you can think is, instead of doing this black box thing, you can basically build a large monolith to deal with everything. Perhaps build this one high performance compiler that compile them all. In fact, this has been the pipe dream for a lot of us. This is what I tried to start in my graduate program when I was a graduate student way long ago, trying to build this kind of monolith compiler. We still haven't been successful building that. We can't have compilers. The only thing we can do like something like that is very domain specific, very narrow things, but the monoliths can't get this kind of performance. The other thing is we write a library that has everything everybody need, every function composition is in there. The problem is there's probably some scientist sitting in some lab somewhere that needs a very weird combination to solve their differential equation. And if you combine everything, you're going to have a gigantic library. This is not practical either. But one of these two observations came about. We know how to do this black box individual kernels and basically compose them. Only problem is there's some locality loss. The question is, can we maintain that composability using black box functions that we know how to do well, but without playing basically the performance engineers can do this, but without playing that cost that we have to incur for locality. That is where Fern comes in. So, Fern is a system we built. It is a very minimalist system. What it did was it enriched the normal function interface. So, it is not going to touch what is written in there, the additional function interface. By using that, we can fuse this code and get rid of that locality. Can we work on chunks in here? So, let us show a little bit what has happened in Fern. So, we have to extend this function interface. So, the idea there is I will tell you how to operate on small chunks of data. So, here what I can say is I am doing some data starting at 0 0, length 2 2 or length 4 2, different lengths in here I can describe that. In fact, if you have more complicated functions, because we are doing this kind of recursively, you can actually compile this and do subset decompositions and come up with hierarchical decompositions of that to describe what is going on. So, if you have something like matrix multiply, this is the additional information you have to say. What you have to tell it is, what I am going to do is I am going to produce this block. To produce a block at xy location with a length x, length y, I need these additional things from A and B. That is one function. That is my data use relationship. And I need a row, I need a column at these places. If I get those two, I can produce that. Then to get all the data, I have to iterate through these blocks, and if I do that, I can calculate the entire matrix in here. And on top of that, I have my previous just description of the function interface in here. That is all I need. So, let us go back to our original example in here. So, this is what you will see today. You have the interface description for the function. We have to add some additional information that says here is the producer consumer relationship in here, and this is basically added to the include file as annotation in here. This is one additional thing we need, and the next thing we have to do is, this is my original function. I have two matrices, two vectors, I doing these two operations back to back. I need to include some additional information around it to say this is little bit of glue logic and say, okay, create these Fern objects and combine them together to run as a one fused function in Fern. This is all you have to do in here. So, you get those things together, and the Fern system basically takes these two, and optionally you can also give little bit additional scheduling information if you want, and it will do few very simple compiler passes. This is not a full compiler, we are just doing very outside thing in there, and then it will generate a small glue logic that will basically execute these two functions in a fused fashion in there, and that is what you run here. So, that is what we can do. So, let me tell a little bit about experiments in this system. So, Intel has this one DNN library that do convolution. So, you can build a DSL that actually do all this fusion, do all these operations and get really good performance. But instead of doing that, you can have very simple convolution, very high performance convolutions implemented, and then get Fern to do this fusion and get good performance in here. Here is another function we could do. This is the same thing that I show at the beginning, but that now you are adding two other matrices to that too at the end of it. It is a much larger function. And the thing about that is nobody has implemented this function in their libraries, because this is probably some graduate student in some corner. It's only one person in the world who probably want to run this function, so it won't be in the library. But if you try to do normal compositions, even trying to hand fuse them, you are not going to get good results. And then in Fern, we can do a much better fusion and get the best possible result in here. So these are what we show as a simple element-wise fusion in here, but Fern can do more. So for example, if you have something like a blur, the X-blur will take in multiple elements out of a row and produce one element. And a blur Y will take multiple elements out of a column and produce one element. And you want to work that together and do blockwise that. In order to do that, there are a bunch of overlapping inputs that you need to deal with, and the Fern description, producer-consumer relationship, can capture that combination in here. And in fact, if you look at a halide, it's kind of a monolith DSL that can deal with this kind of fusion within the DSL. But instead of doing that, I can have a highly optimized row X and Y convolutions, and then basically merge them together to get this using Fern in here. So all these things you can assume, yes, you can build a DSL, it's in the same family. But you can do even across domain. So assume I have a database that I am retrieving bunch of data, and I am going to run a sigmoid function in there. Normally what happens, the database will give you the entire data, and then you run the sigmoid in here. So again, the cache problem at place here. So no database will implement all the functions you want to run with data, so you can't expect that. And the sigmoid library will never implement the database, so you can't expect that. That won't be in a single DSL. But in here, you can get these two different functions very highly implemented, optimized, and then use Fern to basically fuse them together and actually get nice performance in here. So this is great. It's a great story to show for, but there are places where we fall short a little bit. So here's an example in ISPC where, because it has a DSL, it's doing way more than just fusing for caches. It's actually doing vector level vector reuse in here. So Fern, we can't go to the vector level and register level and do register fusion. So they can do register fusion, and by doing that they can get better performance. So that is a place we can't, at a black box level, we don't have access to the register level, so we can't do that. So there are certain things we can't get in there. So it's not a complete panacea, but for many cases this can be very useful. So where I started is with this question: can we build a system that still maintain that opacity and separate created functions and compose them without having any overhead? What we came up with, yes, we can. Probably a couple of election cycles ahead, this would be very cool. So what we have done is we have built this Fern system. It's available online, and in fact there's a newer interface than what's even in the paper in this system that I think is better, and you can go find that there. So what are we working next? We are all in CPUs, so basically what Rohan talked about, we want to go to GPUs. GPUs are actually a lot harder because CPU programming is always take CPU as a virtualized unit. Two things can coexist, time multiplex in there. Only thing perhaps you might not want to give all the processors to each. There might be little bit that you want to share, but mostly it works together. GPUs on the other hand assume when you run something, it owns the entire darn thing. So running two things within is not that easy. So this is a much harder problem. I don't think we can do it completely transparently, because we need to know which memory it is in, what resources it owns matters in low level. You can't virtualize these things, but composition is still very important. So we are also working on how to figure out composing on GPUs. Okay, with that, I'm done.
Hello, Konstantinos from UCLA. Fantastic talk. Yeah, I really believe this. There's a lot of black box composition programs out there, and we need to improve them without, like, going in the black box components. I was wondering about one thing: how complex and how much effort do these annotations or specifications on the functional interfaces that you need to add? How much effort did it take you to write them, or how complex were they, and so on?
for many things, lot of functions are very simple. They are doing almost element-wise things are very simple to deal with. Those things are, I think we can even do lot more automation in there. Then there are next set of functions where what you have is you have lot more complicated data use patterns in that. Okay. Again, they are doing independently, that we can do. The third level of complexity there are internal dependencies. There are orderings that has to happen internally, because there are, you can't just do it any order. Those things we can't do that yet, because so there's a cliff when that happens, because if right now we figure out the ordering of running these blocks, they have to run independently, and they need to produce the same result. But if there's internal state within these functions, black box functions, then we can't do that easily. So I think right now I feel like we are writing more code than necessary. I think for most common cases, 90% of the cases, I think this should be a lot simpler to describe that. I think we have more ways to make it a lot more minimal in there. And also, we probably have to do some more work at the other end when you have a lot more complicated functions that has internal state, internal dependencies, to see whether we can capture that. Those things we haven't gone there, because that to get to that level, I think you need to know something about internals in there. And our hope is, in fact, the person who writes the function should write that interface. Okay, and then the compiler is like, then if it become a standard, like right now a .h file, then the combination would be easier to do.
All right, let's. We do need to run to the next speaker, so maybe, yeah, exactly. So let's thank the speaker again.
Thank you.